All right, well, good afternoon, everybody. In this presentation, I'll be discussing the new calendar date features in C++20 and why they're important for financial programming. Okay, so we're familiar with some of the new C++20 features, the big ones, concepts, modules, and ranges, and they were met with great fanfare and fighter jet flyover and a lot of excitement. But then there were dates. Didn't get quite the reaction. But for financial programming, these should be really, really useful. Main reason is they are critical for anything related to fixed income or bond trading. Just a little history. This enhancement is an addition to the existing Stud chrono library. Howard Hinton is the author, and I just thought I'd give a little shout out to Mr. Hinton and all his group for all the work they put in on this. I think it'll help a lot of financial developers. Just a quick disclaimer. What follows here is just based on my own research and testing, and that's a euphemism for trial and error. I really have not found a whole lot online or in any of the published C++20 books about the new date features, and really next to nothing that's related to financial programming. So what I thought I'd do is just share what I know and what I've learned. And also, just so you know, the objective here is to show how to use these things rather than to get down into the technical details. Okay, so fixed income products, these usually involve a series of payments. So these can be usually monthly, quarterly, semi-annual, or annual. Some examples are coupon-paying bonds. These typically pay a coupon every 6 months. Mortgage and car loans, something that I think some of us are familiar with. You got to pay every month, or else you might have your car repossessed. Annuities, this is where someone, say, wants to have some guaranteed retirement income. So he'll go to the insurance company, pay a lump sum, and then in return, the insurance company will promise a fixed stream of payments. And this can be either over some fixed period of time, or it could be for the lifetime of the contract holder. And these are usually paid monthly and quarterly. Interest rate swaps, this is where a stream of fixed rate payments are exchanged for a floating rate. There are a variety of reasons for this and why people use them. I won't get into them here, but it's a really huge market. And these are usually, what you have is a fixed and float payment usually on the same date, and these usually occur every 3 to 6 months. And then there are futures and options on bonds and swaps. This is also a really big market. Okay, so thought I'd start out with just a quick example about bond pricing. Don't worry, we will get into C++ very soon, but I just thought I'd set this up. So when you buy a bond, what you're doing is you are lending money to either a corporation or a government. This is at issue. After that, they can be traded in the market. So the $1,000 then in exchange for that, you will receive an annual 5% coupon on the face value. And again, bonds are typically paid semi-annually. So the regular coupon date or coupon payment will be 5% times 1,000, then divided by 2 because it's paid twice a year. And then you'll get these coupon payments, say over 30 years, and then at maturity of the bond, the last coupon is paid along with the return of the $1,000. Bonds come with contractual dates. So these are very important. So what did I just do? Oh, there we go, sorry. First one is the issue date, so when the bond is issued. Next is the first payment date, so that's when the first coupon is paid out. Then there's the penultimate payment date, and then the maturity date, where again, the face value is returned along with the final coupon payment. You may notice here that I've left C1 and C60 as unknowns. We'll come back to that. The dates in between are called regular payments on regular dates. So just get the $25 each time. One thing to note here is if any of these payments in between, any of these regular payments, if they fall on non-business days, say a weekend or a holiday, then we need to adjust the date. Usually we just roll forward to the next business day. So again, you can maybe start to see why having dates available when you're programming financial software is really important. Before this, usually what you'd have to do is write your own or find an external library. Okay, so a little bit about the irregular payments and what are called day count conventions. Okay, the first coupon payment date and the maturity date might fall on irregular dates. What this means is the period between issue and the first coupon date might be a little bit shorter than 6 months, and then on the tail end, it can be a little bit longer. So you can see here, there's this, let's see if I can. You can see here, there's this little red line here, so that's the extra time past 6 months. So the way we'll calculate the first payment is we'll just take $1,000 times the 5%, and then we'll just multiply by the time period in, it's a unit of a year fraction. So it can be different from the $25. It is possible that it's a regular payment date, but sometimes they're irregular. On the tail end, what you have is the regular period and then plus a little bit extra. So that means we're going to be paid $25 and then plus 1,000 times the coupon rate and then the time remaining in units of years. Now to calculate these, it's not that simple. And you need to be a little bit careful because there's a contractual day count convention that comes with a bond. They're about the same, but they're a little bit different. A couple of them are actual over 365, another one's called 30 over 360. I'll talk about these in a minute. And there are a number of others. But the point is that it may seem trivial, but you need to get these year fraction calculations correct. If you don't, then another trading desk might figure out that you're calculating your bond incorrectly, and then they can use it against you and trade against you, and your trading desk might lose some money. Okay, so actual 365, this is pretty trivial. It just means you have two dates, date 1 and date 2. You take the difference between them in terms of days, so the number of days between them, and divide by 365. So it's trivial. 30 over 360 is a little bit more involved. What you do is you assume every month has 30 days and every year has 360 days. The formula looks like this. So we're going to need to be able to take the difference in the years of two dates, the months, and the days. And as you can see, we multiply the difference in years by 360, the difference in months by 30, and then we take the difference in days and we divide the whole thing by 360. You also have to account for the end of month conditions. So if the date falls at the end of the month, like you see here, you need to make these adjustments. So as an example, if we take the 6-month period between these two dates, if we use actual over 365, we get something a little bit shy of 0.5. But if we use 30 over 360, we get exactly 1/2. And that's kind of the appeal of 30 over 360. It's simple, and you have, if it's 6 months, it's 1/2. 3 months, it's 1/4, and so forth. Now, the bond price is priced as of its settlement date. And this can be any business date between issue and maturity. So after a bond's issued, it gets traded in the market. So you can buy a bond, and then a month later you can sell it through your brokerage. But the price is not the face value. It's going to be determined by the market interest rates on that day. So here we have a little schedule here. Settlement could be, say, just before the first coupon date. Could be later on. It could fall on a coupon payment date or somewhere else. So as an example, let's take this date here as our settlement date. What we need to do is calculate the value of, calculate the discounted value of each payment. And so that means what the payment in the future is worth today. So we have to apply a discount factor. At the end of the day, there's a little bit more that's involved here, but eventually you get a discount curve. But this is not a continuous curve. What happens in reality is you'll have data points here. So you'll have, say, an overnight rate, then 1 month, 3 months, 6 months, 1 year, 2 years, 5 years, and so forth, 10 years, 20 years, 30 years, and they get wider and wider as you go out in time. So what you need to do is you'll need to interpolate the discount factor from market data. So here's our first payment date. We hit it with whatever this value is here, our discount rate, which we might probably have to interpolate. It's going to be pretty large, close to 1. So what this means is the value of $1 in the future. So in the future, its value declines. And then as we go along, so we do that, and then it gets discounted back to settlement. We do the same thing for the regular payments in between and for the penultimate payment. And then on maturity, we take the face value plus the last coupon payment, and we hit it with a discount factor. And then we take those results and we add them all up, and that gives us a fair price for the bond. So if you're going to buy the bond today, that's what you would expect to pay. But the upshot is this is all dependent upon what the market is saying about interest rates on the settlement date. So hopefully this gives you a little idea of why dates are important in financial programming. So we'll move on now to probably what you came for. Oh, I'm sorry, there's a little thing here. Just reiterating that this is not a continuous curve, but there will be points on the curve and you'll have to interpolate. Okay, so what you've been waiting for, presumably, is a discussion about the actual date features in C++20. So this class, year, month, day, is the workhorse of the date features in stood chrono. It's kind of like what stood vector is to STL containers. That's what the year, month, day class is to stood chrono dates. Okay, so to construct, well, first, before we go any forward, you'll have to either import the chrono header unit, or I don't know why this keeps, I think I'm hitting another button, sorry, or hash include it. There are various ways that you can construct a year, month, day. I'll just show you 2 examples, but there are several more. So first, we just give it a year, month, and day. But you need to put them in as stood chrono objects. They're not just the integer values. So you can see here, we have a stood chrono year, stood chrono month, and stood chrono day, and we instantiate each of these by the respective values. Another thing you can do is use written out months, and these are actually types in stood chrono. So you just give it the year as before, but now we can just write November, and then stood chrono day 14. Of course, in reality, you're not going to be hard coding dates, but it's just for demonstration. There's also assignment, and the way this works is you use the / operator. So one way is similar to the first constructor. We use year, month, and day objects and just separate them with the / operator. You can also just use integers for the last 2 parameters as long as the first one is obvious. So in the first case, this is still year, month, day order, but the first parameter, the year, is obvious. So the compiler will know that means year. And then once it knows that, then it knows the second parameter is month and the third one is year, or is day, I'm sorry. For month, day, year, the first one is obviously a month, then the next parameter will be the day, and then the next one will be year. There are a number of these. There are more that you can look at. This is not an exhaustive list, but you can find them on the Stood Chrono GitHub site, which I've linked here. Okay, another thing that's important though, well, you probably understand this by now, is that we are going to need integer values that are associated with the dates so that we can compute the day count adjusted year fractions. In Stood Chrono, the way this works is the dates are measured relative to the Unix epoch, January 1st, 1970. This is commonly known as a serial date. You may be familiar with this if you've used Excel, where the epoch is January 1st, 1900, and then it just goes 1, 2, 3, 4, and so forth. With Stood Chrono, though, the dates that are before the epoch are represented by negative numbers. So they're still legal, but they just have negative serial numbers. And then the serial date can be accessed as you see here. I'll just go through an explanation of it. You have to do some conversions and things here. So technically what's going on is you have this sysdays operator, and so it's going to convert the year, month, day object to a sysdays object. Sysdays is an alias for Stood Chrono time point. So if you've worked with Stood Chrono at all, you are probably familiar with this. Then by calling the time since epoch function, that will return a stood chrono duration. Again, it's something that you might be familiar with. And then you call the count function on that, and that will give you the corresponding integer value, the serial date. So going back to our earlier example, November 14th, 2002, the serial date would be 12,005. Another thing that we often need to do is to find the number of days between 2 dates. So for example, the actual over 365 day count. So if we take 2 dates, take our original one and then another one 6 months later, it's similar to what we did before, but not quite as involved. You need to convert each date to sysdays, but when you take the difference, this resolves to a duration type, and you can just go ahead and call the count function. And this will return the integer number of days between the 2 dates. What I'll do going forward here is I'll just assume we're using namespace stood chrono We'll lighten up the code a little bit, but I will tell you when there's anything new that we're using from the library as we go along. Okay, we can also access the year, month, and day. Not surprisingly, they're called year, month, and day. However, these are going to return, again, the stood chrono objects, not integer values. You can get the integer values by casting them. For a year, you need to cast it to an int. For month and day, you cast it to unsigned. You can also get the difference between years, months, and days. Say, for example, the 30/360 day count. You just subtract them, and these will return integer values, so you don't have to do any conversion here. One thing you need to watch out for, though, is it is possible to construct an invalid date. This is probably by design, so it doesn't throw an exception automatically if it's a wrong date. But it's left up to you, the programmer, to check. And the way you do this is with the OK member function on the stood chrono date class. So for example, we construct the same date as before. OK, it's true. It's fine. But if you try 31st of February, that's invalid. Call OK, and it will tell you it's false. And you could even enter something just completely ridiculous, like you see here. But these last two statements, these will compile and run. So it's just something you need to be aware of. It's up to you to check. Another thing that often needs to be done is to check whether a day falls during a leap year. And this is pretty easy to do because there is a member function, not surprisingly called isLeap. So you just call isLeap. In this case, it's true. 2016 is a leap year. Excuse me, let me have a little drink here. A lot of times we need to know what the last day of the month is. But in this case, there's no member function available. So we have to do it ourselves. The way we can do this using stood chrono functionality is we create a date, but now we create it as a year, month, day, last type. So what this is, you put in the year and the month, and then you put in this type stood chrono last. And this represents the last day of April 2009. And then to get the day value, you call the day accessor function. And then, as I said before, you can cast these to an unsigned value, and you can get the actual numerical result. It's also implicitly convertible back to a year, month, day. So if for some reason you need to store this on your original date object, you can. However, you might prefer generating or avoid generating this year, month, day, last object and also this assignment. You'd have to, for whatever you're using this with, you'd have to test, see if it really makes a difference. In some of the tests I ran, did this thousands of times, and I did notice that compared to what I'm going to show you, there was a bit of a performance hit. So it's just something to be aware of. And that is a possibility in practice because, say, you're running risk reports, and so you're going to have to price thousands of bonds, thousands of swaps, and thousands of swaptions, all these things. So it can potentially add up. An alternative is to go out to the stood chrono GitHub site again, to the URL you see here, and they provide a set of, as they say, low-level date algorithms. And so these will be a bit faster. a quote from the document. It says, "These are key algorithms that enable one to write their own date class." And that's kind of where we're heading. There are two algorithms called last day of month common year and last day of month. So what I did is I went in the source code and I just combined them and came up with the function that you see here. So we take in a date by non-const ref, and we retrieve the month. Again, we get it by casting to an unsigned. And then we put, this is more brute force. We're not using the stood chrono functionality. We're just putting in the normal any days for each month, so for non-leap years. And then we just check. The only case we need to be worried about is if we're dealing with February in a leap year. Otherwise, it's just we just go up here to the array and get the proper number. If we're dealing with this case here, then we return 29, and we're done. So in this case, you avoid the creation of the extra year, month, day, last object. Okay, adding years and months. This is something that you typically have to do as a financial programmer, especially adding months. The simplest way to do this is to use the addition assignment operator that's available in the stood chrono date class. But again, there's a little extra you have to do here. You have to create these months and years objects. So you just take the year, month, day, date, update it with the number of months, and this is your result, and so forth. But again, you can't just add the integer value. You have to convert to one of these months or years objects before you carry out the addition. And subtraction assignment is also available. Again, a word of caution. When adding years and months, this can also result in invalid dates. So if we have these end of month cases here, so end of January, end of August, and end of February in a leap year, if we carry out these additions, you can see, well, there's no February 31st. There's no 31st of September. And if we go forward 1 year from a leap year at the end of February, we end up with the 29th, which is not valid in 2017. But note that the year and the month are correct, and so we can use this to program a workaround. Okay, for adding years, this is pretty easy. The only thing you need to deal with here is last day of February, so that's pretty easy. A bit more difficult is dealing with adding months because you have all these different months with different numbers of days. So what you can do is just naively attempt as before, check if it's valid. If it is, return the result. If not, grab the year and the month, and then update the day. So here's a little function that does that. So we take in the date object and the number of months we want to add, proceed naively here, and then just check if it's valid. If it's not valid, then it's because we have an end of the month issue. So that just means correct the date so it has the proper end of the month. And we can call this program that we looked at just previously, and it will return the proper last day of the month. And that fixes that problem. For adding days, there is no addition assignment operator. So in this case, you're back to converting to sys days. So it's the same kind of thing as before, but we add stood chrono days and with an argument of 3, so 3 days. And again, this is implicitly convertible back to a year, month, day object, so you can reassign it. Okay, so now let's look at wrapping all this stuff in our own date class. So what we're going to do is encapsulate the complexities and some of these special conditions that we need to deal with. We're just going to wrap it inside our own class. So all that stuff that we did to adjust and so forth, it'll just be done for us. But first, let's revisit the typical requirements that you need for dates in financial programming. Okay, first there are states that we might want to check. One is the leap year. The other is how many days are there in a month. The arithmetic operators, as before, so we want to be able to find the number of days between 2 dates, and then we need to be able to add years, days, or months to a date. And then accessors, year, month, and day, but what we'll do here is we will return integer types rather than the stood chrono object. Also, you'll often need to have the serial date representation, so that will be available. And it's sometimes convenient to actually be able to access the underlying year, month, day member object. We'll also have to program a modifying function that will roll to the next business day if a date falls on a weekend. And then we'll need comparison operators because we need to know if one date is later than another and so forth. But if we look at this, these 4 items here we already have. We've done these. So we can just take them and wrap them in a member function. There's some more that are represented by that little Pac-Man figure. It's like 3/4 done, so almost done. A little bit more work to do. The one function that we'll need to implement from scratch, though, will be this, this weekend roll. Okay, so again, you need to import or hash include the chrono library, and I'm just going to use a namespace alias here just to make things a little simpler. So if we look at the declaration of the public methods, I've just put into the declarations what we had on the previous page. So it should be pretty self-explanatory. A couple of things here, though. The equality operator and the spaceship operator are already implemented on the year, month, day class. So it's just a matter of wrapping those. So that's no problem. And also there's a stream operator, and we can do the same thing. So you can output dates to the screen. The one thing that we need to do is implement this weekend roll function. Sorry. Okay. As for private members and methods, we'll need to store the stood chrono year, month, day object and the corresponding serial date. So the serial date will be set at construction, and then anytime the date is modified, say we add months to the date, then we need to update the serial date. And we can do that by calling this helper function called reset serial date. For constructors, I've put in 2. What we'll do here is take in the year, month, and day as integer types. By integer types, I mean it could be int or unsigned. Again, in stood chrono, years should be ints, months and days should be unsigned because that's the way that they're cast. Check if the date is valid, and then as long as it is, then we call the reset serial date function, and it will set the corresponding serial date. Default constructor will just default to the Unix epoch. So this is just serial date 1, so you just initialize it. The reset serial date function, it just takes essentially what we had early on. So we need to convert to sysdays, then call time since epoch, and then we call count to get the actual integer value. Difference between two dates. Now we'll do this a little bit differently. Because we're storing the serial dates, we can just take the difference of those. All right, so the serial date on the one date and the one that we're subtracting. This way you can avoid these function calls. I don't know if there's really a big performance issue here or not, but the code is cleaner. And also just in general, in financial programming, this is usually what's done. The business day roll, this is the last thing that we need to do for our class. So this says, if a transaction, actually this is incorrect, a contract date will never fall on a weekend because you wouldn't set up a contract with a wrong date. So that's a typo. But if a transaction date falls on a weekend, we're going to apply what's called the modified forward rule. There are 4 different roll methods that are commonly used in finance. The one that I've seen the most is called modified forward. And what that does is it will roll forward to the next business date. But then you need to check, does it roll forward to the next month? And if that's the case, then you roll back to the last business day in the original month. So here, what we're going to do is we're going to use another class in Stud Chrono called weekday. Now, this naming is maybe a little bit misleading. That does not mean weekday as in Monday, Tuesday through Friday. What it means is day of the week. We'll also want to store the original month because we want to check whether we roll into the next month or not. So we create a weekday object called WDN. I'm sorry, we have that up here. We can get the day code by calling this function that's on this weekday class called ISO encoding. And it will return an integer value corresponding to day of the week. And that goes from Monday equals 1 through Sunday equals 7. And then to check, we just check if it's greater than 5 because 6 and 7 are Saturday and Sunday. And if so, then we just subtract that value. So 6 is Saturday, 8 minus 6 is 2, so we roll forward 2 days. And similarly for Sunday. But then we need to check, do we roll into the next month? And so this is why we stored the original month here. And then we compare with the updated date. The other thing that you need to check is because January is 1 and December is 12, the inequality here won't apply. So we need to check this as a special case. And if this happens, then we just roll back from the Monday that we've rolled to the previous Friday. This will work for weekends. Usually, in fact, almost surely, you'll need to deal with holidays. That's a bit more involved. Really don't have the time to deal with it here, but you could apply this, but suppose you roll back to a Friday and the Friday's a holiday. So now you got to deal with that. But for our purposes here, just for demonstration, we're just limiting it to the weekend case. Because we have modified this date object, we'll need to reset the serial date. And then we're done. Okay, here's one place now where we can apply use of our date class back to good old day counts. So define an interface class, as you see here, with an operator, and this will just take in 2 of our chrono date objects, so date 1 and date 2. and it will return the day count adjusted year fraction. For actual over 365, again, this is trivial, but because we have subtraction defined as the number of days between two dates, it makes it trivial. And divide by 365, and we're done there. For 30 over 360, again, it's a bit more involved. So what we'll do first is implement a helper function called dateDiff. And what it will do is calculate the numerator of this formula here with all the constraints that you see down here. Then we'll take that value and then just divide it by 360, and we're done. Okay, so to wrap up, this isn't the most exciting topic in the world. I'm pleased to see that you're all still awake, so it's good. But it is absolutely vital when you are working as a financial programmer, because you're going to have to deal with fixed income products. And there are other products as well, where where dates and day counts can matter. I'll also discuss a few other things that you would typically need to do as a financial programmer. But it's really great now to finally have a proper date class in C++. As I said before, we either have to write our own or find an external library. And as I said, this is especially crucial for any type of fixed income or fixed income derivatives trading. But do be aware that it is possible to instantiate invalid dates. And so it is up to you, the programmer, to check that. You just use the OK function on the stood chrono date class. And then what we did is we took the year, month, day class and wrapped it in our own user-defined class. So this gives us year, month, day representation. And we can also get the corresponding serial date. We can check whether the date falls in a leap year, whether it's valid, and we can access the number of days in a month. We also have accessors for year, month, and day, but these will return integer values, so that's probably going to be a bit more convenient for us. And we can also calculate the number of days between the two dates with the subtraction operator, and we can add years, months, and days. Adding months is especially important because, as you saw before, we had that schedule of payments, right? So you're going to have to add 6 months all the way out to 30 years. So it's convenient to have that. We also have the business day rules for weekends. And again, remember, this would also apply to holidays, but it's just a little bit more work. It's more than a little bit, but it basically works the same way. But you need to bring in a holiday table. That's usually the way it's done. You have to keep track of these for if you work in the field. You are often going to be dealing with international investments and trading. So you need to have a holiday table for each country. So it can get a bit messy and tedious, but again, it's absolutely essential. We have a arguably more intuitive interface. We're just taking integer types. We don't convert to the stood chrono types. We let the constructor take care of that for us. And our class will just handle invalid date classes internally. And if we try to construct one, it throws an exception. Okay, then we looked at one application of using our own class, or our own date class, And that was in the day count classes. So 2 dates, find the year fraction between them according to a given day count convention. But there are other problems that are a lot more interesting. One is writing a yield curve class, or classes, because there are going to be different types of yield curves, different types of interpolation. You have to put all this stuff together. It's an interesting problem. Also, you might want to you also might want to write a bond pricing class. So all that stuff that we talked about, you just put it in a class. You give it the 4 dates. It constructs the object. And then to price the bond, you give it today's yield curve and the settlement date, and you get the price. And there are also often bond analytics like duration and convexity, that sort of thing that you might want to put on the class. And then there are interest rate derivatives pricing models. This is where the math gets really, really interesting. So if there are any mathematicians here, you would probably enjoy working in interest rate derivatives. But even with all that sophisticated mathematics, and talking stochastic calculus, measure theory, all this stuff, you still need good old dates. So even with the most sophisticated machinery, you can't get along without them. Okay, well, that pretty much wraps it up here. I did it again, sorry. These slides will be available through the usual CppCon source, but I will also put them out on my own GitHub, repository. I also have some sample code that accompanies it. It's done, but I really need to tidy it up first, so give me another week or 2 to do that. If you'd like to remind me to get it done, you can contact me here, or if you have any follow-up questions, feel free to find me on LinkedIn, or here's my CppCon email address. So anyway, that's it. Thank you very much for coming. I hope that was reasonably interesting. So, thank you very much. So, yeah.
Hi, I was curious, do you know why the standard allows certain invalid dates to be representable as opposed to making them impossible to actually construct in the first place?
Not sure I understand. You can create invalid dates. So
yes, the question is, do you know why that is a thing
why
that is
that
allowed?
is.
Like, is there any utility? Is it prohibitively difficult to disallow representing dates like that? Because it seems like a meaningful amount of tedium to have to consistently check that your dates are
sure, and
valid before you use them.
That's why I put that into the date class. So we check at construction. Let's see where it is here. So here we check right here if it's okay. So you can do that, yes. I don't know for sure, but I'm assuming the reason it was designed that way is so it doesn't just automatically throw an exception. You may or may not want to. So I'm assuming that the library designers leave it up to the programmer to deal with that. So, any other questions? Yeah, sure.
So do you know how far back you can go in time? I know in finance it's probably not relevant, but in other fields it may be relevant to go
it's
hundreds of years back.
I think you can. It represents the entire, or you can get any date in the Gregorian calendar. So.
Okay, thanks.
Please, there's an online question, and I'm going to read it to you.
Okay.
The person says it's a non-C++ question. You said the bond price depends on interest rates on the settlement date. Do you mean interest rates on the trade date? If not, what am I missing? Thanks.
I'm not sure I quite understand the
Okay, let me
question.
read it again. You said the bond price depends on interest rates on the settlement date.
Right.
Did you mean interest rates on the trade date?
Well, the settlement date is I'm assuming settlement and trade are the same date.
Okay,
So I hope that answers that question.
all right. And then the second question is, beside the weekends, there's also the banking holidays to consider.
Right, and I mentioned that. Yes, you need to consider those. And that just involves a bit more work and can be a bit tedious, and we'd probably be here for another 20 minutes. So I just left it out of the presentation. But yes, you do need to deal with those. It's very, very important. Okay. Is that it? All right, well, thank you very much.